Hey everyone, today we are going to break down one of the most elegant and widely used algorithms in machine learning, the Naive Bayes Classifier. By the end of this video, you will understand exactly how it works. So what exactly is Naive Bayes? It is a supervised machine learning algorithm used for classification tasks. What makes it special is that instead of just giving you a label, it actually calculates the probability of a data point belonging to each class using something called Bayes theorem. You will find it everywhere: spam filters in your email, sentiment analysis, document classification, even medical diagnosis. It is popular because it's simple, fast, and surprisingly effective. Now let's look at math behind it. Don't worry, it's simpler than it looks. The core formula is given here. Let me break down each part. P of y by x, the posterior. Given that I saw a feature x, what is the probability the class is y? P of x by y, it is likelihood. If the class is y, how likely is it to have feature x? P of y. Before seeing any data, how likely is class y? P of x, the marginal. How common is feature x overall? The classifier basically asks which class makes the observed feature most probable. Here's where the naive part comes in, and it's actually the algorithm's biggest assumption. Naive Bayes assumes that all features are completely independent of each other. In reality, that's rarely true. Classic example: classifying a fruit as an apple based on it being red, round, and sweet. These three features are clearly related to each other, but Naive Bayes just ignores that. This is trade-off. It's an oversimplification, but as we'll see, it still works remarkably well in practice. Alright, let's make this concept with a classic example: spam detection. Imagine we have 10 historical emails, 4 spam and 6 ham. Ham is nothing but not spam. We are tracking just two words as features: win and money. From the data, win appears in 3 out of 4 spam emails and 1 out of 6 ham emails. Money appears in all 4 spam emails and 2 out of 6 ham emails. Now a new email arrives containing both win and money. The question is it spam or ham? Let's calculate. Step 1 is computing the prior probabilities. Basically, what's the baseline chance of any email being spam before we look at words? Probability of spam is equals to 4 by 10. Probability of ham is 6 by 10. Step 2 is computing the likelihoods. Given a class, how probable is each word? Notice how money appears in 100% of spam emails. That's already a huge signal. Now the final step. We multiply the priori by all the likelihoods together. This is the naive independence assumption at work. Spam score is 0.30, but ham score is 0.033. Since spam score is greater than ham score, the model classifies this email as spam, and it is correct. Notice we didn't even need to compute P of x, the denominator, because it's the same for both classes. We just compare the scores directly. So why should we use Naive Bayes? There are 3 big reasons. 1. Highly efficient and fast. It needs very little training data to estimate parameters and run extremely fast, making it ideal for real-time systems. It handles high dimensionality and multi-class prediction. But It is not perfect. Here are the key limitations to know. The independence assumption fails. In real world data, features are almost always correlated. On highly correlated datasets, the assumption can seriously hurt performance. Zero frequency problem. If a word appears in the test set but never appeared in the training, the model assigns it a probability of 0, which kills the entire calculation. The fix is Laplace smoothing, which adds a small count to every feature. And the last limitation is the poor probability estimator. It's often a great classifier, but the actual probability number it outputs are generally unreliable. Don't trust those raw scores as true probabilities. So to wrap up, naive Bayes is a beautifully simple algorithm. Yes, its core assumption is naive, but that's precisely what makes it fast, scalable, and easy to interpret. It remains one of the strongest baseline models in machine learning, especially for NLP tasks. Whenever you are tackling a classification problem, naive Bayes is always worth trying first before jumping to heavier models. Thank you.